It is my pleasure. It is my pleasure to introduce today's speaker, Professor Feng-Yu Wang from Tianjin University, with the talk Entropy Estimate between Diffusion Process and Application to McKean-Vlasov Equation. Please, Professor.
Okay, thanks a lot for the invitation. It's my pleasure to give a talk here. So today I'd like to talk about entropy estimate between different diffusion processes. So the idea is using this estimate to establish so-called cost entropy cost inequality for McKean-Vlasov SDE. This is a joint work with Pampa and Zheng in City University of Hong Kong. So this outline, first of all, I talk a little bit about motivations, as I mentioned, to establish the log hierarchy inequality for distribution dependent SDE, also called entropy cost inequality. It turns out we will use entropy inequality by Bogachev, Zokala, and Shelp-Snikov. Then I will explain there is an essential difficult to apply the inequality. So then to overcome the difficulty, we introduce a trick we call it by coupling argument. Coupling means we construct two processes, then look at how fast they meet together. So by coupling means we indeed construct three processes. So the third one will be coupled with each of the first two ones. So this is a trick I will explain. Then with this trick, we are able to estimate the entropy by Western distance for distribution dependent SDE. So then introduce the main results and schedule proof. So now, as I mentioned, the point is we will estimate entropy by Western distance. I think everybody here should know this already. We look at the space P2, which is the set of all probability measure on RD having finite signal moment. Okay, so there is a natural probability distance on this space. There are, of course, many different names. Normally, people call it Western distance, denoted by W2. From optimal transport theory, this means the optimal transportation cost to transport a distribution from mu to nu was cost rate distance squared. So then another notion is relative entropy, which is again measures how far is one distribution to the other. So if you look at the relative entropy of a measure nu with respect to mu, by definition is nothing but if nu is absolutely continuous with respect to mu, so then it is defined as a log of the density with respect to nu. Otherwise, the entropy is infinity. So there is an inequality. Now people call it Tanner-Grant inequality, published in 1996. He looked at the mu is just the standard Gaussian measure, RD. He found that for this kind of mu, any distribution nu, the W2 square is bounded about by 2 times entropy. Okay. So this inequality is in extended to more general situations. Here is a general result, which says if a reference measure mu, which could be different from the Gaussian measure, any probability measure mu, if it satisfies the so-called log super inequality, okay, the entropy of f squared mu with respect to mu is bounded out by the energy up to constant C. If this inequality is true for some probability mu, then the Tanner-Ground type inequality is true for the same constant C here, W2 squared bounded by C times entropy. This general result first proved by Otto Villani in 2000, and a curvature condition. So because here we only look at RD, so the curvature on the space is 0, but for the operator, there is minus Hessian bounded below by K. Then in another paper by Bobkov, Zandil, Duo, they drop this condition. So they
Excuse me, can I have a question?
Yeah.
Am I right that such measures which satisfy this condition sometimes is called logarithmically concave?
Right. So if a measure mu satisfies this noticeable inequality, then this Tanner-Ground inequality holds. This is a theory found by Otto Villani. Of course, this is more general than the original Tanner-Ground. Okay. So they proved under this condition, minus Hessian bounded below. But in this paper, next paper, this condition is dropped. Okay, so this becomes a general result. So then the idea for present for our study is try to prove the inverse inequality. Say we try to bound the entropy by W2 squared. Okay, somehow it's an inverse Tanner-Ground inequality. But in general, this inverse inequality couldn't be true, because if you look at measure nu, which is singular with respect to mu, the entropy will be infinity, but the W2 could be finite. So therefore, in general, the inverse inequality is wrong. However, if we look at a nice process, say in the beginning, the entropy could be infinity. Entropy of nu with respect to mu could be infinity. So there is no chance to bound about by W2 squared. But if we run these initial distributions by a nice process, okay, look at a stochastic process. PT star nu just means the distribution of the process at the time t, whose initial distribution is nu. Okay, it's just a notation. Then at the time t, the distributions, we look at the entropy, could be bounded about by W2 squared for the initial distributions up to some constant Ct depending on t. So if t should be positive, okay. If t goes to 0, this Ct should go to infinity. So this is a kind of inverse Tanner-Ground inequality for a micro process. So this entropy-cost inequality is equivalent to the following, we call it log hierarchy inequality. So if you denote PTF of some probability mu as the F integral with respect to mu PT star mu. So then this inequality is equivalent to PT log F at a measure nu bounded about by log PTF mu. We exchange the order of log and PT. Then was an error term, same as here, CTW2 squared. So this kind of inequality goes back to one of my papers published in 2010. In this paper, I look at the diffusion process on the many manifold. Okay, the generator is Laplacian plus a drift. I proved that if the curvature, this curvature minus Laplace z is bounded below by a constant minus k, if and only if the entropy at the time t is bounded about by the W2 squared for initial distributions up to a constant, depending on t and the curvature of k. They are equivalent to each other. Then, since this paper, this kind of inequality has been extended to some other models like SDE, SPD, and also distribution dependent SD, like this, also called McKean-Vlasov SD. So here, if we look at the evolution of a process xt, so it equals to a drift dt, then a noise term sigma t. The point is both drift and noise coefficients depends on the distribution of the xt. L xt means distribution of xt. Without the distribution term, it goes back to a classical Ito type SDE. So here B sigma maps defined like this. Okay, WT is noise borne motion. Then again, if this McKean-Vlasov SDE is well posed, then we denote PT star mu as the distribution of the solution at time t was the initial distribution mu. Okay, again use the same notation here. Then our purpose is to prove the same type estimate, entropy-cost estimate. So for small time, the behavior should something like a constant over t, like here, like in the diffusions and manifold. Here, okay. So here for small time, it behaves like a constant over t. So for non-degenerate SDE, we should have similar estimate like this. So this our purpose is to estimate entropy like this for distribution dependent SDE. Then again, this remark, okay, this inequality equivalent to this log-Hartley inequality. Indeed, there are already some results for distribution dependent SDE. For example, if the noise coefficient doesn't depend on mu, it only depends on time and space variable x, then the log-Hartley or entropy-cost inequality already exists. Another situation is noise coefficient only depends on time and mu, but independent of x. Then again, the log-Hartley inequality already exists. However, if sigma t depends on both x and mu, then the existing argument, we use so-called coupling by change of measure argument, does not work for this more general situation. So in this talk, we use different technique to establish the log-Hartley inequality. So now I'd like to explain the study indeed goes back to entropy estimate between different diffusion processes. Because for different initial distributions, the PT star mu by definition is distribution of solution to this SDE with the initial distribution mu, okay? So because this SDE depends on distribution, so for different initial distribution, the SDE indeed are different. This is just because of the distribution dependence. So therefore, for fixed mu, we can replace by definition, the distribution part is nothing but PT star mu. If we already solved the SDE, okay, we just replace the distribution parameter by PT star mu, which is now given. So then the same for the drift. So with this notation, the McKean-Vlasov SDE can be formulated as classical SDE. But the point is coefficients depends on mu now. So for different mu, the coefficients are different. So therefore, to estimate the PT star mu and PT star nu, the entropy, which means we are estimating the entropy between different diffusion processes because the SD are different. So therefore, in general, we can look at two different diffusion operators for each R equal to 1 and 2. We look at the second order differential operator, AUT, AR, with.
Excuse me, can I have a question? Can you show up the previous slide, please? You froze this mu t and nu t measure-valued processes. Then you get coefficients which definitely depends on omega through this mu t and nu t. Am I right? Or you just say that let they be deterministic?
Right. So here, so if you look at the original SD here,
Yes.
here the parameter is distribution of solution.
Yes.
Also, we already solved the SD. So by definition,
Yes,
distribution.
suppose that we solve it, yes, and then let's go back. But yes, this is my question. That after this, maybe we cannot say that a process which is the solution of such equation xt is a simple diffusion process because the coefficients are random. Yes.
Coefficient is not random.
So we just
so
this PT mu is deterministic now, yeah?
It's deterministic, it's distribution.
Okay, thank you. Okay.
Not random. Okay. So now it's clear. So the point is we only need to estimate entropy between different.
So two different diffusion processes.
Right. So in general, we look at two different second order differential operator like this. The second order coefficient is AI and the drift is BI. Suppose for any initial distribution nu, this operator generates a unique diffusion process. I denoted by xt I nu. So I just means the I process. Nu is the initial distribution. T is time. This is clear. Then simply denoted by pt I nu, the distribution of the process at the time t. Okay. So if it is absolute continuous, I denoted by small p, the density of the distribution. Then the inequality by Pugachev, Rucker, and Shapsnikov, published in 2016, is the inequality like this. So they only look at the entropy between two diffusion processes was the same initial distribution. Okay, you see the two processes have same initial distributions, nu. Then at the time t, the entropy between the distributions is bounded about by 1/4. The integral from 0 to t expectation by this A2 is the second diffusion coefficient. But we put the first diffusion process inside. Then we assume it's non-degenerate. So there is -1/2 here. Then another functional phi nu is defined in this way. You can imagine this entropy should be bounded about by some difference between the coefficients. So therefore, phi mu is difference between A1 and A2. Here is the singular term, gradient of heat killer for the first process. Then the other term is divergence of A1 minus A2 and the difference between B2 and B1. Okay, this just the inequality. So I put the gradient log PS in red because this is singular. For example, if nu is just Dirac measure, so at time 0, PS equal to 0, the density doesn't exist. So therefore, there is a singularity when S equal to 0. So now, this is a proof. Maybe I simply just show quickly. So the proof is indeed quite straightforward. Okay, so maybe I just pass it. So now I like to show the difficulty. So now come back to the inequality here. The point is there is a singularity term, gradient log Hildekin. So in general, so if you estimate the upper bound, so the norm, because A2 is non-degenerate, okay, it is reduced to the norm square of phi. So the other two terms in phi, you can assume they are bounded, okay. Then the only singular term is here, gradient log PS. So in general, for example, if nu is just Dirac measure, okay, so then it's well known this gradient log Hildekin behaves like S2 minus 1. S2 minus 1 is not integrable from 0 to t. So therefore, in general, this upper bound could be infinity. Of course, it also could be finite. For example, if initial distribution is good enough, has a density zoo, and the entropy of zoo is finite. In this case, this one is finite. The upper bound is finite. But for our purpose, we will allow arbitrary initial distributions. So therefore, for arbitrary initial distributions, we couldn't apply this estimate direct, otherwise the upper bound could be infinity. So then to overcome this problem, we introduced another process. You can regard as the interpolation process of the initial two different diffusion processes. Now the coefficients, diffusion and drift coefficients of the new process is the following. If we want to estimate the entropy at time t1, for example, we choose a smaller time t0 before time t1. Then we define coefficients A and B as follows. So before time t0, we choose A1, B1, choose the first process, okay? After t0, we take the second coefficients. So then it's clear the new coefficients AB is nothing but some kind of interpolation of original coefficients. Then I denote by PT nu1 the distribution of the diffusion process generated by the new operator with the coefficients A and B. Here nu1 is the initial distribution for the first process, for the post process. So now I allow the original two different diffusions having different initial process. Okay, for the first one, initial distribution is nu1. For the second, the initial distribution nu2. Then we can estimate the entropy as follows. For any p bigger than 1, it's bounded about by p times the entropy between the first process with respect to the interpolated process. This is the third one we just construct, okay? So then plus p minus 1 times log of this density of pt nu1 with respect to the second process with some power p over p minus 1, okay? We integrate with respect to the second distribution. I will show this inequality in a general framework. Once we have this inequality, it turns out for the first term, we are now easy to apply the inequality by Bogachev-Zokhin and so on. Because in this case, you see the coefficients between AB and A1, B1 becomes 0 before T0, okay? So therefore, if you apply this inequality, then here becomes, before T0, the coefficient, the distance here becomes 0 because the coefficients are same. So therefore, the singularity of the gradient log P is for S less than T0 disappear. Okay, if you the integral only exists from T0 to T1, in this interval, the gradient log of heat kernel is uniform bounded under certain conditions. So therefore, for the first term, we can apply the inequality to derive a non-trivial upward. Now the point is, how can we estimate the second term? It turns out the second term goes back to the so-called Halaki inequality with power. It's again one of my previous result, originally published in PDIF 1997. Okay, what you see is again for diffusion process on remaining manifold, okay, generated by Laplace plus drift Z. The diffusion semigroup satisfies this kind of Halaki inequality for any P bigger than 1, if and only if the coefficient is bounded below by some constant minus k. So here, the P is some constant bigger than 1. Then by move the power from outside to inside, we are able to move the PTF from X to Y. Okay? Then now the error term becomes exponential, some constant times rho is distant, remaining distant. The distance between X and Y squared over some constant depending on time and the coefficient k. This again sharpen inequality because it's equivalent to coefficient. Then the point is this inequality indeed equivalent to the following inequality. So this, if this inequality is true, then the PT X, which means starting from X, point X, the distribution of process at time T, PTX, will be absolutely continuous with respect to PTY, and the density to power P over P minus 1 integral with respect to PTY will be bounded about by this exponential, the same exponential term. You see, this is exactly the one appear to the second term. So which means we will apply, because from at the time T1, the new process generated by with coefficient AB is the same as the second process, because at T1 from T0 on, the coefficient is equals to the second. So therefore, you can imagine here could be replaced by P T12. The second process was different than the initial distribution, new one, okay, with respect to the second process was the initial distribution, new 2. So it's nothing but exactly equality here. So therefore, with this idea, we can already estimate the entropy between two different diffusion processes. So now I quickly prove this inequality I mentioned before. So in general, for any measurable process, measurable space E, any two probability measures mu1, mu2. If you like to estimate the entropy between mu1 and mu2, you can choose a reference measure mu here. It is bounded about by p times entropy of mu1 with respect to mu plus p plus 1 times log of this one. Okay, just as I explained in the previous slide. The proof is more or less easy. Point is, if you look at the difference between these two entropy, by definition, if we just assume the density all exists, otherwise the upper bound is infinity, the equality is true, okay? If density exists, by definition is nothing but a log of density integral. Then you just put them together, it becomes a log of d mu 2 in d mu 1. Okay. Then you can replace d mu 1 by d mu 1 over d mu 2 in d mu 2. So here in the log, we put a power here. So to cancel it, we put another p minus 1 over p in front. So then now just Young equality. You see, already gives the proof. So now the idea I already explained. Now just formulate the main results. Of course, we do need some conditions and coefficients to estimate the entropy. Condition is the following. We will allow the drift BI to be daily continuous with respect to some daily function. So it's not necessarily Lipschitz, even not necessarily Hölder continuous. So daily function is some phi, which is increasing concave 0 at 0, such that phi s over s is integrable from 0 to 1. Then for any function on the time space, then given time t, if t infinity just means the uniform norm of ft, so the supreme over x, okay? So for a smaller time r, smaller than t, r to t infinity means the if s infinity norm supreme over s on this interval from r to t. Now, if we look at f 0 to capital T phi norm, which is now the norm, the linear continuity norm here. So the first term is uniform norm. The second is linear continuity, continuous module. F x minus fy over phi at distance xy, take a super. So this is just notations. Then now conditions on the coefficient. For each r, br is decomposed into two parts. The first one, br0, could be singular. Then br1 is Lipschitz term, which means there is a constant k such that br0 is bounded. Okay. But the gradient of br1 is bounded, which means br1 is Lipschitz continuous. Then for ai, for the noise coefficient is just bounded, and the inverse is also bounded. The gradient is also bounded. These conditions on ai and bi. In addition to these conditions, we need to assume one of the bi0 should be daily continuous. Under this condition, we can bound about, we can find a constant C and also a constant epsilon less than 1/2, such that for any two different initial distributions, the entropy between two different diffusions can be bounded about constant over T, W2 squared. So this is what we want, okay? But here we look at the arbitrary two different diffusions. So the difference between coefficients will be also involved in the upper bound. So it is integral from 0 to T, the difference between drift square and also difference between noise coefficient square. Additional term is now A1 minus A2, the uniform norm from epsilon T to T square. Also, the integral from epsilon T to T, the divergent uniform norm square. Here, the derivative is bounded, implies that this is bounded, okay? So remark is this first estimate already extend existing results for one process, okay? If we look at one process, but it was different initial distribution, then the entropy from here, the entropy is bounded about by C over T W2 squared. Because if the generator are same, then all the other terms are zero, okay, already recover the entropy-cost inequality for one process with different initial distributions. Of course, in this case, if we only look at one SDE with different initial distribution, B0 could be even more singular, just to satisfy some local integrability condition. So another assertion is if the coefficient for the first process satisfies this first and second derivative is bounded as well. So then the estimate can be improved like this. The improved part is here. So this uniform norm for the difference between A1 and A2 can be dropped. So as application, we can look at now log-Harlock inequality for McKean-Vlasov SDE, as I mentioned before. The point is if we look at the entropy for distributions with different initial distributions, then you go back to the entropy between two different diffusion processes with coefficients like this, as I mentioned before. For fixed mu on the path space from 0 capital T to P2, okay? We now denoted by mu, B mu, the drift SBTX now replace the distribution part by mu T here. Okay. So for A, use the same notation. So in application to this McKean-Vlasov SDE, mu T will be PT star mu, as I mentioned before. So now our condition is the following. To apply the last result, the condition for the coefficients in this McKean-Vlasov SDE will be something like the following. So again, for each mu, so A mu and B mu will satisfy the following conditions. B mu again decomposed into different parts, B0, B1. Then the B0 part is a bounded part. And here we need it to be Gilly continuous, okay? Norm was a Gilly continuous function phi here is bounded about. Then for the B1 part is regular part, gradient is bound. And for A, it is non-degenerate, uniform elliptic is bounded, and the inverse is bounded, and also gradient is bound. The same as assumption A, but applied to the present framework. Then the third one is new. The third one gives the Lipschitz condition for the coefficients in distribution, which means if we fix time and also space variable x, but just look at the difference between with different distribution parameters. Okay, the noise coefficient, also drift coefficient, and also divergence of the diffusion coefficient will be Lipschitz continuous in mu and nu W2. So this just Lipschitz dependence of coefficients. Then now the assertion is the following, and the condition B, the McKean-Vlasov SDEs will pass. And also there is a constant C such that for different initial distribution, if we look at the entropy at time t, which will be bounded by constant over t with W2 squared. This is exactly what we want. Now the proof is very, very easy. So according to the first process, you look at the PT star mu and PT star nu. It is now distribution for two different diffusion process with the coefficient B mu, B nu, and A mu, A nu here. So just use the estimate in the previous result. So then it turns out the besides the W2 square, all other terms is bounded by this supreme of W2 PT star mu, PT star nu. Sorry, there is a type. Here should be PS star mu, PS star nu for OS, supreme over OS. This is the biggest, okay, dominate all other terms. Then we can also prove this W2 PT star mu and PT star nu is bounded by constant times the W2 square for initial distributions. So now the proof is just finished. So then now I like to briefly introduce the proof for the first result. Now look at again two different diffusion processes. Remember now the interpolation process, the generator is given by A and B like this. Okay, so as I mentioned, now for simplicity, I only look at the initial distribution, the fixed point, starting from fixed point. Then the entropy will be bounded by the first term is entropy for the first process and the third process here. The second term is something like this, okay? So the first term, we can apply the inequality by Bogachev and so on, which will be bounded by this one. This is a singular term. The other term are a good term, means which can be bounded easily. So therefore, if this is bounded, so then the only point is to estimate the integral from 0 T1 to epsilon T1 to T1. Then here, gradient log P1 square over P1. Okay, so the whole point now is only to estimate this term. So now here is the result containing upper bound of this one. So and the condition A, there is a constant C, such that for any r smaller than t, the integral from r to t here is bounded by constant times log 1 plus T1R. Then if the coefficients for the first process are good enough, such that the first and the second order derivatives are bound, then the estimate can be improved for single t. We already have this kind of 1 over t estimate. Maybe I simply pass the proof. The idea is using an heat killer estimate in this paper. So which means for and condition A, the heat killer for the first process has this Gaussian type up and lower bound estimates. Okay, theta is solution. Is flow generated by B1 coefficient. So then together with this estimate, the entropy is bounded about by minus constant. This is what we like to estimate. Okay, once we have this, the integral part will be bounded about by the entropy part. And here, from this heat killer estimate, you see the entropy is bounded from below and above by something like log T2 minus T over 2. So this gives exactly what we want. Okay, if the coefficients are good enough, it's bounded first and second order derivatives, then just by Malliavin calculus, which is a topic of the seminar, we have the integration by pass formula. For the first diffusion process, the semi-group of gradient F can be formed as expectation of F xt, then times some martingale. The martingale is has a second moment bounded about by a constant times t minus 2. So this implies what we want. Okay. So in conclusion, we already estimated the first term as we wanted. So for the second term, we use a result by Pan Zheng. So she proved that under even more general condition, so the drift could be more singular. She proved that this Halaki inequality was power already true. If you look at the semi-group of the second process, because it's time inhomogeneous, so I denoted by P, we have two different time parameters, epsilon, which means the semi-group from epsilon T1 up to T1. Okay, look at this time interval. It is F2 minus 2 power at one point here. I put the first diffusion process as the space variable inside the semi-group here, which is bounded about by I move P inside, P power inside, then we move the space variable from this first process to the second process. Okay, then the error term is exponential to some constant distance square over time t1. This just the Halaki inequality with the power, the same type as I mentioned in Riemannian manifold. But for singular SD, this also holds. Equivalently, we have this estimate. So it turns out we, in the second term, we take expectation of this one and take log, right? So the expectation of this one will be bounded about by expectation of coefficients like this. So to prove this estimate, we do need one of the singular drift BI0 is daily continuous in X. The daily continuity is used here. Once this estimate is true, the second term, because we also take log of it, second term will be bounded about by something like this. So put them together, we finish the proof for the first result. Okay. So then I also like to mention some further results. The idea is the same using bi-coupling argument. But in this paper with Xin Huang, we can establish the same inequality with more singular situation. Here, for example, the drift and the noise coefficient. Here is a break list here. They are also Lebesgue continuous in distribution, but with respect to a bigger distance, not just with respect to W2. So here the big distance is W2 plus some W psi. Psi is a function. Psi square is Dirichlet function, so which means psi could be even more singular than Dirichlet function. Then W psi is a distance induced by the cost function psi of distance. This one paper to improve a little bit and now more singular situation in distribution. And the other paper was Zhongmin Qian. We look at the degenerate models. You see, if we come back to the inequality by Bogachev and so on, so we do need the non-degenerate property, which means the coefficient. The diffusion coefficient is non-degenerate to make sure the inverse here, A2 to minus 1/2 exists. So therefore, this inequality only applies to non-degenerate SD. But in other paper, we extend the idea also to degenerate models like this. This is an example. Of course, the general result applies also to other degenerate models. This could stochastic Hamiltonian system, which is also distribution dependent. First coefficient, there are two different components, okay, of the product space. For first component, there is no noise. In physics, it means the location of particle. The second y is the speed of the particle. There is a noise here. Then also in the second component, the drift and the noise depends on the distribution. Then finally, just some reference I mentioned in the talk. This is a paper by Bogachev, Rokler, Shaposhnikov, and the heat killer estimate from this paper. The Halaki inequality with power from paper by Pampazin. And this paper was Xin Huang. We prove the log Halaki inequality for McKean-Vlasov SDE with coefficient only depends on time and law and the distribution, but independent of x. Okay. In this paper by myself, the log Halaki inequality is established for the noise coefficient only depends on t and x, but independent of mu, as I mentioned in the beginning. Okay, so this is all for my talk. Thanks for your attention.
Thank you very much for very interesting and detailed talk. And maybe somebody have questions or comments, please.
May I ask a few questions? So my first question is very technical question. I try to follow your talk very carefully. Could you go to the condition number 3, where you had the assumption on the difference of coefficients, and you said something about this difference in terms of the measures mu and nu. It seems that you already skipped that because it was in the middle of your talk.
So Not this condition.
So a little bit down. So there were three main conditions which allows you to formulate the main statement. It seems one slide before, or even no even. So it was that conditions were before you formulated the main result. You showed actually the idea of proof, how you can deal with the term which has a gradient of logarithm of the density. After that, you formulated so a little bit more down, more. No more. More.
This is for McKean-Vlasov.
It seems that that is the assumption number 3, and I always thought in the terms of the McKean-Vlasov equation, and here I mean in the McKean-Vlasov equation you denoted by B nu and A nu. It is just the coefficients where the solution is frozen, where the distribution of X is frozen, right?
Just in the distribution parameter, it just replaced by mu or nu. So this is just a notation. So therefore, this condition is just a Lipschitz condition.
It is only Lipschitz conditions with respect to only that slot where we plug in the solution, where we plug in the distribution of the process X, or it is like Lipschitz condition.
Yeah, it is Lipschitz condition
with respect to the initial distribution of the process. Okay, it is only Lipschitz. Then I have no questions. Okay, good. Okay, that is clear for me.
Thank you.
And the second question is, it is like more conceptual question. I know that now in mean-field games, the McKean-Vlasov equations with common noise is very important and well studied. Actively studied now. Could you say anything whether your idea could be extended, I mean, to this situation when we have also the second noise and we consider the conditioning, the conditional distribution?
Sure, very interesting question. Of course, it's also interesting or important to look at with common noise situation, McKean-Vlasov with common noise. I guess in that situation, you can do the same thing for the conditional distribution. The PT here is defined as a conditional distribution given the common noise. So perhaps you can do the same thing.
But at the moment, an analog of Sapochnikov and Röchner result is unknown, right? Because your approach is based so much on it.
Right, but in this case, there is no common noise. Now PT star mu is just the distribution of the solution.
Sure.
If there is another common noise, you can define this as a conditional distribution, given the common noise. Okay, you still use this notation, but it becomes random. Maybe you can look at the same property. I'm not so sure, but maybe you can try or can think about this. So for common noise situation, this should be conditional distribution, right? Given the common noise. So then somehow this becomes a measure valued process now. But still, you can estimate the entropy.
Yes, and as Professor Drogosh mentioned it, so now it would be the coefficients which depends also on omega. So therefore, you have to do something with that.
Sure. So then it's will be not exactly classical diffusion process, but SDE with random coefficients. Yeah. But the technique should also work. You can think about maybe can extend to that situation. Yeah, very nice question.
Okay, thank you.
Some other questions, please. I also have some questions. The first of all, since you can estimate the relative entropy for measures of the solution, for distributions of the solution, it is maybe good to think about large deviation theorems, because relative entropy naturally arise in Sanov theorem, and from other side, one can get McKean-Vlasov equation as a limiting case for system of interacting particles with identically distributed independent noises.
Yeah, it's a very, very interesting question. For large deviation, there are different type, of course. So maybe I don't know what you mean. Non-time, Donsk-Weidan type.
Yes. I mean the theorem like this. Suppose you fix t time, and then you approximate your McKean-Vlasov equation by equation for discrete family of interacting particles with independent noises. You just get the empirical distribution of these particles. You know that it definitely tends to the limiting distribution, and you know the speed from Sanov theorem. You can try to get the same as in Sanov theorem for empirical measures, or Donsker-Vardan, of course, for empirical distributions, because you have already estimation for speed function. It will be interesting.
Yeah. This will be very interesting. Yeah. We can think about it. Very nice question.
Also, let me ask you about the condition of the diffusion coefficient. Do you suppose that it is non-degenerate?
Yeah, in this talk, I only look at a non-degenerate situation.
Okay, so what about Hermander conditions?
Yeah. So this is the other table. You can find already. We put already our table here. This table.
So.
We use some kind of a Hermander condition for degenerate.
But no, yes, I have seen this example, but it seems to me that it is not rather general. I am asking about the general Hermander condition for one equation for x, LTX, and suppose that sigma satisfy Hermander condition. I think that it can be done because all what you need is the smoothing properties of the semigroup.
Right. You are right.
Yeah. Then we can guarantee Bogachov, Ryokhner, Shapashnikov, and your log Harnack inequality.
Right. Yeah? Exactly. Indeed, in this paper, we first of all prove a very general result. This is just an example.
I see. Okay, so you have general.
Yeah. For the case you mentioned, the coefficient of noise already satisfy Hermander condition. The general result.
Okay, good. And then the last one is related to Vitali equation because usually we prove that semigroup has smoothing properties under Hermander condition using Malliavin calculus. Then maybe when you have this colored noise, of course, you will have not diffusion processes, as it seems to me in the beginning of your talk, but you still can use Malliavin calculus and check some analog of smoothing properties. Yeah.
Exactly. Right. So indeed, the point is, for example, in this paper, the point is to use Malliavin calculus establish integration by path formula like this.
Okay, thank you very much again for interesting talk. This is your first talk at our seminar, and I very hope that it is not last talk at our seminar. Please attend it and came to us with new interesting results. Thank you very much. Also, I have an announcement that next week we have a Ukrainian-Uzbekistan conference, so the seminar will not hold. but the week after week we have seminar, and maybe Georgi know who is the speaker.
The speaker will be Mykola Vovchansky.
Okay, thank you very much. Thanks everybody, and see you after 2 weeks. Bye.
Bye bye.
Goodbye. Goodbye.
See you. Bye.
Bye.
Bye. Thank you.